This is actually recording for real this time. I'm not forgetting and I'm not messing it up. We're really recording. Mwah. Okay. All right. So we've introduced in this reading, we've introduced a really important concept and we've introduced really important notation. What is the concept and what is the notation that we were introduced to in the reading that's due today? Yes, Avon.
Well, the concept was like the function.
Yes.
And then the notation was like y equals x, and then like in parentheses x.
Or f.
Y equals f in parentheses.
F of x, yes. So if we're thinking about doing a graph, again, often we're labeling this x, this y. We've talked a lot about parabolas. Last time we spent some time like sketching the graph of different parabolas of the tennis ball, and it looked, something like this. We could say, we can label this f of x because it's the function. Okay, very good. Now we get into some more specific questions in this problem. For example, when we got to sort of our little unit one, our little example one, and we had questions A, B, C, D, and E. So let's just go ahead and go through those together. And so let's just go ahead and A, B, C, D, and E. Does anybody want to, let me know if you would like to sign up to share your answer to one of these letters. Yes, Jelena?
Oh, like are you asking like individually or just like as a class?
Well, you're going to be the one to explain your answer to the class.
Oh, yeah.
Do you want to do one of these?
Sure.
Which one?
Anyone really.
Anyone really?
Just give me a random one.
All right, I'm putting, your hand was up first, so I'm putting your name up first. Yes, Avon?
I'll do B.
Avon's on B. All right. Who's on C? Walter?
Wait, I have a question.
Yes, Milo.
On Google Classroom, it says to do page 327. I just looked over page 327.
Yeah, that confused me, but then I was like, I don't see any blue boxes, so I turned the page.
Turn the page. Oh yeah, we read 327 in class, and we talked about doing 328.
Yeah.
Okay.
So it's just a matter of turning the page to include that following problem.
Yeah.
And I'm sorry if I mistyped that. Now, when you saw that, did you put a comment in Google Classroom saying, Ms. Ferris, did you mean page 328?
No, I didn't.
Okay, so when little confusions like that come up, then I would say, please let me know right away.
Destination 1 with blue text on it, so I assumed that's what you meant by blue box.
Yeah, I see what you mean. I see what you mean.
I thought you meant the blue box was 331, then I talked to Avon and he was like, no.
It was 328, yeah. So that was my mistake. But again, if you feel like you're having to make assumptions, assumption is the mother of all mess ups. So then in that case, I would say it's really easy right on the assignment in Google Classroom just to be like, wait, Ms. Ferris wasn't this 328, and then I would look at it and I'd be like, oh yeah, that's a typo. So, because we don't want to leave little questions like that until class if we can avoid it. Yes, Jelena?
I
Yeah.
don't know.
Yes.
There's also a blue box in 327, so, yeah.
Yeah, I think this is
We did that in class.
Yeah, we did that. Yeah, we did that in class, and we talked about doing 328. We talked about in class doing 328, and then I did a typo when I put it on Google Classroom. So, yes.
How would you just like when it says like for mine, it says like F50, like do you just or would I just say like F50?
Oh, that's a really good question. So this written like this, we would say f of
F of 50.
50.
Okay.
Yes.
Got it.
Yep. Good.
Thank you.
Yeah, no, that's a good question. All right, anybody else for D or E?
I guess I can do it.
Okay. All right, I'll go ahead and put myself down
Yay.
for the last one. Okay, so Jelena, let's look at 1A.
Okay. It's how is the fact F of 50 equal to 64 shown on the graph?
Yes.
So, I went to the graph, went to 50 on the vertical drop, and I went estimated where 64 would be. And I put, it is shown by the intercepting points on the graph. That's what I put.
Yeah, that makes sense. And so, and how did you know to go to 50 on the vertical drop and then look to see where that was on the runtime?
Well, at like the part above number 1, I read that, and then it was. It's a good question. I guess I could just assume.
Yeah.
I guess 'cause that just makes the most sense to me.
Yes. Well, and in fact, that is good, and your intuition is on point, and also your reading of the explanation is on point, which is that you go to, if you have f of 50, then you're looking for 50 down here, and then seeing approximately, and in this case you kind of have to approximate,
Yeah.
that this is 64 here. Now, it's kind of approximating on the graph because we don't see the number 64 over here.
Yeah, it's kind of easy.
Yeah, but is there a way that we can confirm that? Because is the graph the only piece of information that we're given?
No, you can also use the chart.
Yep.
So basically, just yeah, look for 50 in the vertical drop, and then approximate in runtime, and say it should be 64.
And then we can see, yeah, it's not just kind of, we can confirm, it doesn't just look like 64 on the
Yeah.
graph. We can see that it matches the data that we have in the chart. Perfect. All right, excellent. Stop. All right, Avon, B.
Yes. That's funny. Okay.
Oh yeah, your last initial is B. All right, yes.
So my question was, what value of y satisfies the equation y equals f function f is like f 40?
F of 40.
F of 40.
Yes.
What? Like so. Then I went to the table, and then I saw vertical drop in meters was I went to 40 there, and I went over, and it had a runtime of 71 seconds. So why for that situation be 71 seconds?
That's exactly right. So we can find 40 on the data table under vertical drop and see that a drop of 40 corresponds to a runtime of 71 seconds. Very good.
Yeah, that's fine.
Smiley face. All right, C, Walter.
So my question is, what value of x satisfies the equation 51 equals f of x?
Okay.
So I went over to the, not the graph, but the table, and looked in the runtime, and found 51, and across from it is 80. So,
There we go.
F of 80 satisfies y equals, yeah, 51 equals f of x, sorry.
Very good, excellent, okay.
You got
Oh, you got a
Four leaf clover.
clover.
All right, yes, Milo.
Try E when we get to it.
Yes.
What if we do W if it goes up there?
Maybe like,
Don't want to ruin our experience entirely. Oh wow. Oh no.
Rolling eye.
no, I'm not gonna lay that guilt trip on anybody. Okay, so very good, that's right. So we can see that sometimes we can also go the other direction, meaning if we know what the what value we ended at, we can back up to it and find out what was plugged in. Awesome. Okay, how about D, Liam?
What value of y satisfies the equation y equals 10? So what I did is I looked for the number 10 somewhere on the graph, and then when I found the 10, I looked to the opposite side and I saw 143.
Very good. I think that you guys are getting the hang of this. So that's right. If we want to know y equals f of 10, we look for the 10 vertical drop and we find the runtime of 143. All right, so Milo, part E.
Wait, don't I get a
Oh,
symbol?
shoot.
Oh.
Yes.
Do a butterfly.
Soccer ball. Bounce and pound.
Oh, I don't know if I can draw a soccer ball. Peace sign. Peace. All right. And, all right, Milo.
So the equation is 45 equals Fx, and 45 is on the runtime for the bottom one, and the vertical drop will be 100.
That's right. Very good. So that's the very steepest, fastest one. Very good. Let's see. There you go. All right, excellent. Okay, so we can, I think you guys have done a good job showing sort of the x's and the y's, and we can see those on the table, we can see them on the graph, and the f of x is really the relationship between them. Yes, Avon.
What is the relationship?
So that's a really good question. It's interesting to me that in the book we picked a kind of equation that we're not going to get to later. In this case, this particular graph that we have, that looks like this is actually a logarithmic function. So logs are something that actually we'll get to next year. So in this particular case, this graph, the relationship between the numbers is logarithmic, and this shape of the graph that kind of looks like an L is it's kind of a hallmark of what a logarithmic graph might look like. However, when we consider, let's go ahead and look at the following, let's look at the, continue on and look at the bouncing balls example. Yeah, so that's the one that we've actually been spending more time talking about recently. We can see that the ball is bouncing in a parabolic fashion, which means that here, this f of x is going to be some flavor of ax squared plus bx plus c.
Because it's more parallel than like this. Semicircle.
Well,
Yes.
it would be just a extension graph. It's not any flavor of that. It'd be specifically on the graph.
Yeah, well, yes, but part of it also depends on like how bouncy is the ball? Did somebody just drop it or did they throw it down? So there are other things that, that can influence exactly what the equation of the parabola is. But definitely the major factor that's causing this to be a parabola is the force of gravity. Okay, so what I'd like for us to do, and so this will be a good opportunity to add some things to your notes. So make sure that you have got your any notes handy from the conversation that we had in the prior class, the prior couple of classes, about parabolas, about the beginning of this chapter, and we're going to add some other stuff on there. Okay, so here's the graph of the bouncing ball parabola example that we have and this was sort of this logarithmic graph that we had with the luge course height, vertical drop versus runtime. And here's another graph that we can do of another shape that's very familiar, a circle. And we can graph a circle on the coordinate plane. And if we know the coordinates of the center, we can also write the equation of this circle. We usually label the center of circle HK. But we can say that x minus h squared plus y minus k squared equals r squared. In other words, we can have the equation of a circle and we can graph it on the coordinate plane. So here, this purple guy, the equation is probably going to be, this is probably going to be, f of x is going to be like,
Is that an R or an
this is an r. We're just going to go ahead, f of x equals log of x. This isn't, like I said, we'll get to exactly what this is next year. We're focusing right now on y equals, or here we can say f of x equals ax squared plus bx plus c. So we've got the equation of a parabola. This is going to be some kind of a logarithmic function.
What's a logarithm?
Logarithm just kind of has this shape.
Oh,
Yeah, we'll get to it next year. And then we can also have the equation of a circle. Now, two of these are graphs of functions, and one of these is not. They all have an equation, but not all of them is a function. So what I'd like you to do is to take a couple minutes and to jot down what you see in these three graphs, what the similarities are, what the differences are, and see if you can identify which graph is not a function, and what your guess is for that, and then what about it is different than the other two. And once you have some ideas written down, then compare, we'll do this for just like 30 seconds, and then compare with your neighbor.
Can you repeat that again?
Yes. So right now we have three graphs of equations on the board. We've got ax squared plus bx plus c. We've got log of x. And we've got x minus h squared plus y minus k squared equals r squared. And all of these are real equations, and all of them are equations that we can graph on the xy coordinate plane. So there's nothing about that part that's like a trick question or something like, oh, ha ha ha, this one's not actually an equation, or something like that. So they're all equations, they all have graphs, they're all on the xy coordinate plane, but one of these is not a function. So what I want you to do is to look at the features of what's graphed up here, identify similarities and differences between the three graphs, and see if you can figure out which one is not a function and what makes it different from the other two. just by looking at the graph. Then once you have some answers written down, so it'll take 30 seconds, and then you can compare with your neighbor.
Oh, like look at the graph, not the equation.
You can look at the equations too. Yeah, so you can try and distinguish, okay, what are the features of the graph, what are the features of the equation, how can we tell which are functions and which is not a function? One of these guys is not ever going to appear in a chapter about functions.
I think.
Well, don't give it away, but write down your ideas on it, try and be specific, and then compare it to your neighbor.
What if you have like two separate theories?
That's okay, write them all down, write down all your theories, and then we can discuss.
I review monologue. One of the two.
I haven't seen a clean car from back yet.
Favorite person was just at that place for one day.
In the rain. Maybe they just have like tons of cars, and they just come in the car that was in it.
I think it's more likely that they just can't once.
What about the possibility if they have multiple cars?
That is a
Possibility that they come at different times.
That's the
Alright.
other possibility.
Maybe they're just renting the car for the day.
That's also
For a
a possibility.
day.
Yeah.
Then you can just take the bus.
Or
It's
walk.
a fun car.
Or for a week, they could, we don't
Okay.
have it, just for a week.
All right, have you compared with your neighbor?
No.
Which, alright, so.
Yeah.
The one that's
Yeah.
What do you?
The green, the black one, the purple, and
It's not
Have we
exactly
gotten to your-
Am I correct?
Have we gotten to your question, Akumi?
Exactly.
Have we gotten to your question that you had at lunchtime?
That's what they say.
Yeah, okay.
not a
They cut the different.
Good.
Woo, I'm right. Where is it? Yeah, that's what I put. Woo, I love being right.
You don't know if you're right.
Okay, that is our turn.
You're wrong.
Yes, that is our square, yes.
Well, I have two.
Oh, I'm pretty sure we're right.
I'll go with both.
So,
All right.
it's okay, we're right.
Probably. But,
Well, then we are definitely right.
All right, who would like to share a theory first? All right, I saw Jelina's hand first again. She is up there with the quickness today.
All three of us think got the same thing. Well, basically, I think it's the circle because one, it doesn't have FX, but then two, unlike the other ones, it goes back to itself, and then the other ones, they kind of like don't, and they touch like the axes
Well,
or the.
yeah, no, that's a good, this one.
Oh, that one not
doesn't.
necessarily.
That one doesn't necessarily, that's right.
Yeah.
But this idea that this one kind of like starts coming back is, and that there's no f of x here, good observations, yes, Avon, and then Walter.
One of my theories was also that because it didn't have the f of x, but then another one of my theories was that it's the ax squared thing because it's like bouncing and it's not like a consistent curve and doesn't like have a pattern. Like it has a pattern, but it's an inconsistent pattern and therefore it's not a function.
That's true. In fact, this one is going to, to actually produce this graph is going to require something that's a little bit more complex than
Yeah.
this.
So,
So,
I don't know. That's my theory.
yes. Good. Walter, what else did you want to
so
add?
the addition I have to Julina's thing is that the circle doesn't because because right there, if say beyond the circle's thing, say if the circle's here and there's an X thing over here or a Y down here, it doesn't involve a circle. And so it doesn't, a function has to be, if X equals this, Y equals this, but if both X and Y don't have anything with the line, any relation with the line, then
That-
nothing counts.
So that's a really good, that is a really good, important clarification that I want us to come back to. What time is it? 1:35. Okay. At 1:45, I want you to remind me to come back to that point, Walter. Because we're gonna need to get a little bit more sophisticated answer than that, but that's also a really important point. Yes, Jelena.
Okay, this may have been Walter was the same, but is it because it's not is the circle
like it can, yeah.
It's like continuous, so does that have something to do with it?
So that, and that's a very, it's not exactly the same, but that's a very related question to what Walter asked, and this idea of what are the boundaries, like can a function have boundaries, what are they, and it's very clear, the fact that this is so contained definitely sets it apart from these other ones, which in theory they could just keep going. Okay, now this purple one is based off of a luge course. Can the vertical drop actually go, because remember, how long is the course? Not how high is it, but how long is, it's 1,000 meters. So can this actually go forever?
No.
To the end of the universe? What's the actual maximum?
1,000 meters.
It's just straight down. So you just, I don't know. That would be extremely scary.
Yeah.
That's a bungee jump. That's not luge anymore. You better make sure you're anchored to the top because that's a bungee jump now. That's not a luge. So this idea of sort of like what are the parameters around a function? Is it only a function if it goes to infinity? Those are really important questions. We will come back to that. What I will start by saying is, good job, everybody, with your observations, and you are correct in that this is the guy who doesn't belong. Okay? He does not have an F, so there's no f of x. Y is not alone. That's another clue. We don't have y equals something. Y is also kind of like in the midst of the mishigas of this equation. Yes, Milo?
So why do we need the circle there?
Well, because it is helping to illustrate this idea of just because something has an equation doesn't mean that it's a function. Okay, let's go ahead and let's just plot this on the same graph as our f of x graph. I'm going to go back to our original question. So we're going to go back to 1a, and I'm just going to move this here a little bit. And we're going to say that this is 50, and we could check here that when we plug in 50, over here we got 64. When we plug in 50 then to this circle equation, what do we get out?
Two numbers.
Yeah. So I don't know, we can guesstimate, I don't know, maybe that's 80 and that's, I don't know, 150. So when we go up here, we hit the graph twice. And this gets to your idea of like, wait a minute, this one's kind of like doubling back on itself. If we can put in one number and we don't know what's going to come out, it is not a function. So a function has to be like a recipe. If you put the ingredients together in the right order, put them in the oven at the right temperature and set the timer, it's not gonna be like 25 minutes later you open it up and it's like, oh, it's chocolate chip cookies, or oh, it's a roast Kahlua pig, or oh, it's a wedding cake, or a sofa. Like, it's not gonna, when you open up that oven door, it's not gonna be a surprise.
It shouldn't be a surprise.
It should not be a surprise. If you do the instructions and you follow them as written, if you put the cookie dough in, when the timer goes off, 12 minutes later, you get the chocolate chip cookies out. You know based on what's going in, what's going to be coming out. That is a function. This situation where it's kind of like, well, we don't know what we're going to get, that is not a function. So this is why, does anybody want to guess when we're looking at a graph what the test is called to see if the graph is a function or not?
Graph
It is what?
X equals 0.
Well, you guys are kind of on the right.
I said graph test.
Yeah, you guys are on kind of the right line. I'm looking for something. that I can use, I'll use this right here. The graph is actually called the vertical line test, because if you can run like a scanner, a vertical line from left to right and never touch the graph twice, then that means the graph is a function. And it's because when you put one thing in, you get one thing out, period. It's predictable. But we can see when we do the vertical line test, the circle fails the vertical line test because there are many places where if we put one number in, we're getting multiple numbers out.
In fact, there's only 2 places where that doesn't happen.
Yeah, exactly. Right here and right here. Yes, Jelena.
So, how we do the test is just like if the line goes through it.
Yes. So
The
if
line
you,
goes through the circle though.
well, we can see like on the purple one, the line, this vertical line, like this scanner, it's never touching the purple graph more than once.
Oh, so okay.
So as long as it's only touching the graph once,
But with the circle.
but with the
it's always
circle, like here, it's touching just once at the very edge, but now from here, it's touching at the top and bottom, and here, you know.
Yeah.
And so,
I guess
if
the
there
answer
were,
is-
have any of you guys ever played the, it's not really a board game, but it's just kind of like a parlor game, Taboo,
Yeah.
where you're trying to get the other person to say a word, but there's like 5 words on a card you're not allowed to say, and somebody else has the buzzer, and so if you say one of the disallowed words, you get to like hit the buzzer on them.
Yeah.
It's really loud and annoying.
My family.
That's the sound I imagine. It's just like, hey, you know, it's just like this does not pass the vertical line test. Okay. However, yes, Akumi.
Okay, so I did this during Algebra 1, and now I'm just remembering all of this.
Yes. No, and there will probably be quite a few things in this class that some people have seen before and some people vaguely remember, and there'll probably be other things that people like definitely remember. And then there will be other things that's like new to everybody or new to certain people. So some of this will be review, some of it will be new.
The only reason I had any sort of memory of this is because during Algebra 1, which was, oh yeah, 2 years ago, 8th grade.
Yeah.
We finished the curriculum like 2 or 3 weeks early, so my Algebra 1 teacher just started going into other
Introducing
stuff.
some additional concepts. Yeah, I love
Yeah.
it when that happens. Okay.
And I still remember the quadratic formula.
Excellent. Okay, but Walter, ooh, I'm gonna get to it 2 minutes early. Okay.
Yes, that's
There's actually more like 30 seconds early.
Okay. I guess it depends on.
Okay, guys. Are we
Which
gonna
clock
do it
are we
next
looking at?
week?
yes, definitely.
And now basically it's only 10 seconds.
Mine says 20 seconds.
Well, yeah, guys, leave it alone.
So we're gonna look at something that we know is definitely a function. Because it's one that we've been looking at in a few different ways. So here are f of x equals ax squared plus bx plus c. So we have a parabola. We can see this passes the vertical line test. And these little arrows here at the top, what do those indicate? Yeah, to infinity and beyond. And beyond. So the graph just keeps going. So we can ask the question, so this gets to the idea of sort of like bounds and restrictions and limitations on a function. In other words, does the function have to be able to go everywhere to be a function, or can it have limitations? Okay? With the circle, we could see sort of like extreme limitations in basically every direction. But let's consider, and again, we have to remember that this is just continuing going. Okay? So let's first look at this graph horizontally. Are there any x's that we could pick where we couldn't find a y? In other words, is there any x that we couldn't then go from there and then connect to the graph, Akumi?
Vertex.
Well, here, this vertex is sitting right here, but does this have a y value?
No.
Well,
Yeah.
what, I mean, so this is a difference, is there a difference between 0 and nothing, or 0 and absent? That's kind of a tough philosophical question. But if it's sitting right here on the x-axis, you know, I don't know, let's just say that this is 10. Is there a y coordinate for this 10? And if so, what is it?
0.
Yeah. So actually, 0 does count as a value. There's a difference between the number 0. So 0 is not the same thing as like NA, or does not apply. So we can say here, we've got no limitations on x. We can see whether we go down here, if we pick this number down here, eventually we can go up and connect with the graph and find out what the y is. Here we can see, okay, it's 0, but that is still, 0 is still a numerical value, as opposed to like not, like there being no available answer of any description. And we can see as we keep going over here, yep, we can eventually, if we pick this number and plug it in, we'll be able to go up and connect with the graph. Now let's look at the graph vertically.
Yeah, there's a lot.
There is, yes. So what is the vertical limitation on this graph?
0, below 0.
Yes.
That's
But
the
we
same
can
for
say
0.
that y cannot go
Wait, why can't it?
below 0. So let's look at, let's go back to one of the questions from the homework. Let's look at, Walter, did you do C?
I did, yeah, I did say C.
Okay. So for C, we picked a y, and then we could back up to find out what the x is. So like, for example, if we pick this y, we can go over here and find out what the x is. All right. But let's say that I pick this y, and I try and go over here to connect.
But X is not going to be.
There's no x. There isn't any x here. So a function does not have to be sort of like limitless in all directions. It can have constraints. It can have limitations. And even with like our purple graph of the luge course, that could still be a function even though the luge course is only 1,000 meters long, and therefore it will have a hard, like the graph will come to an end at 1,000. That is now vertical drop. There isn't anywhere else to go from there. So a function can have limitations, but what it can't do is double back on itself. Yes, Akumi.
I've got notes that I need to use. Can I go do that right now?
Yes. So probably nobody has heard of these vocabulary words before. But does anybody know by chance, there's a specific word that talks about what x's are allowed, and a specific word that talks about what y's are allowed for a function. Okay, we're gonna drop these in here too. No limitations on x means that the domain of x, and here we can do a capital R is all real numbers. There are no limitations on x. But here we can say the range of y is greater than or equal to 0.
What?
Wait, what's that thing to the
Yeah.
right of x?
This is a capital R.
Oh.
Oh,
So to write a capital R like with a pen, you can just do a double vertical line.
why? Like why?
No, no, X. No. This and this capital, this capital R stands for all real numbers. So this is just another sort of like notation.
Okay, but I
So
mean,
domain of X, and you could just write this, the domain of X is all real.
Can you also just do a regular capital R?
yeah.
No,
Okay, so that weird capital R.
this weird capital R, yes.
Oh.
This bold capital R stands for all real numbers. In other words, there's no limitations on X. So for this function, we can plug in any number, any positive number, any negative number, we can plug in 0, and we will be able to get a Y value out of it. We can calculate an f of X. But we do have limitations on our Y. We can't pick a negative Y and then back up over here and find out what the X value is. There is none. So this means the range of Y is that it has to be greater than or equal to 0. Yes, Jolena.
I was just asking what that meant.
Yes. So the domain, so
Oh,
this,
no, not that.
Oh,
I was
yeah.
just wondering what the, I totally forgot about the.
oh, greater than or equal
I'm
to?
terrible at it, so I was like, what is that?
This is greater than or equal to. So in other words, Y can be equal to 0, Y can be a positive number, but Y cannot be a negative number. But even though there are limitations, this is still a function because it passes the vertical line test. How about if I draw the parabola like that? That's still kind of a parabola shape.
But what about the scanning thing?
Yeah, the scanner is going to start beeping here, and it's just going to beep until the end of all time. So this is this is not a function. So
So does this work for all functions or just this specific function?
this meaning,
Like the most, like no limitations on that, just this.
well, so let's think of, this is a really good question. Okay, so let's now look at another one that we looked at was, we looked at a cubic equation. Is a cubic equation a function? So who says no?
Oh, not me.
Wait a minute. So does this pass the vertical line test or not? It does pass the vertical line test. It gets steeper and steeper, but it's still continuing. It's not actually going straight up. It's just the slope is getting steeper as it's continuing to go up and to the right. And here the slope is getting steeper as it's continuing to go down and to the left. Okay, so this is a cubic equation is a function. So remember, this was y equals ax cubed plus bx squared plus cx plus d. Yes, this is a function. It passes the vertical line test.
Wait, can you repeat that? I can't.
Yes. So this is, and I can write this a little bit more clearly here. This is y equals ax cubed plus bx squared plus cx plus d. So this is a cubic equation. This is this was the graph of when we did the volume of the boxes. This is a function. This passes the vertical line test. Okay, so now we'll come back to this idea of the domain and the range. can we plug in any x to y equals x cubed?
Yeah. Yeah.
Yeah, we can plug in negative numbers, positive numbers, 0. So again, there's no limitations on x. The domain is going to be all real numbers. Okay, now on a parabola, y couldn't go below 0. There are no y's down here. If we try and back up into an x from down here and we go over, we're not going to hit the graph. But how about for y equals x cubed?
Yeah.
Yeah, we can go down here, we can find out what this x is. So y equals x cubed, the domain is all real numbers, the range is also all real numbers. So sometimes the functions, there are no limitations. They are going out infinitely. It encompasses all x's, it encompasses all y's. But we can see here with the parabola, sometimes there are limitations. Sometimes there are parameters, but they can still both be functions. So that's a really good clarification.
I have no right to do, but you can.
All right.
You have to print all. History seminar.
English.
That's true.
Yeah, it's fine. It's distraction, but it's a good distraction.
All right. So our next assignment is going to be
Like this?
Our next assignment is going to be continuing with some of these observations and questions about functions from the chapter. And you can pick 2 from 2 through 6. Now this is tough because now I'm looking at a different book from you.
Do like 2 of the problem.
But you can do, so starting on page 328, which has number 2 in the blue square,
Yeah.
and then continuing to 329,
Even 3:30.
and then continuing through 330, there are another 2 through 6 sort of like exercises, like groups, like clusters of questions around a scenario. You need to pick 2 of those between 2 and 6, just 2. So you can look at them and read them and see which ones you find interesting.
When I come with questions and answers.
Yeah. And so that is what we are going to be working towards for Wednesday's class. So continuing exploration of this. Now this time I will be really careful not to put typos in the instructions. Sorry about that, everybody. Well, because it should have been 328 and it said 327. But hopefully everybody's hearing me though. We're going to be picking 2 problems of the remaining ones that are in this section of the chapter that we will talk about in class on Wednesday.
Can I do all of them just for fun?
If you want to do more, you're welcome to do more, absolutely. But everybody needs to pick at least 2. Great job today, everybody. Thank you.